This video tutorial is on chemical nomenclature. The word nomenclature essentially means naming system. So in this video clip we'll be learning how to name different types of chemicals and also write out their formulas. Now, different cultures have different naming systems. So for instance, if you see a certain name, like this one over here, Liu Ming Wai, chances are pretty good that you can determine what culture this naming system is from, or what type of name this is. And chances are it's probably going to be Chinese. Similarly, different types of chemical compounds have different naming systems. And by looking at the chemical name, you can gain insight into the type of substance and its physical-chemical properties. So the first naming system we're going to be looking at is for ionic compounds. These are compounds that generally form between metals and nonmetals. So if you see a compound that is comprised of an element on this side of the periodic table, bonded to an element on this side of the periodic table, chances are pretty good that it's going to use this naming system. So this naming system follows the format of element, elemenide. So let's take a look at these two examples over here. So the first one is Na bonded to a Cl. Looking at the periodic table, you can see that sodium is over here on the metal side, and chlorine is over here on the non-metal side. So yes, they are definitely a metal bonded to a non-metal, so we can use this naming system. As I said before, the naming system follows this format: element, elemenide, meaning that the first element, you don't change its name, you keep it exactly the same. So for instance over here, Na, you write down sodium. However, the second element does change its name. It's like in a traditional marriage, the wife changes her name, whereas the husband doesn't change his name, in a traditional marriage, of course. So over here, this used to be called a chlorine atom, but now we changed the name from chlorine to chloride. And that's pretty much it. Let's try a second one over here. So we got magnesium and a bromine bonded together. Looking at the periodic table, we see that magnesium is definitely on the metal side, and bromine is definitely on the non-metal side. So it's a non-metal bonded with a metal, and that way we are allowed to use this naming system. So first up, the metal, magnesium. The metal does not change its name, so we write down magnesium. However, bromine is the non-metal, and bromine will change its prefix, or suffix rather. All right? So it used to be called bromine, but we need to take out the last suffix and replace it with an IDE. So we call it a bromide. The problem a lot of students have with this naming system is when to put the IDE, or where to put the IDE in. All right? So how do I know it's chloride? Why isn't it chlorine-ide? I'm sure there is some sort of grammatical rule for it. Unfortunately, I have no clue what it is. I just know if it sounds right or it sounds wrong. For instance, chloride sounds right to me, not chlorinide. Which one sounds right to you? Brominide or bromide? Or, for instance, with oxygen, is it oxygenide or oxide that sounds more correct? So to assist you with this, I have created a list of all the nonmetals you're going to come into contact with. So take a moment to memorize these guys and get a feel for how they are pronounced. So for instance, this one's carbide. It used to be called carbon. So carbon turns into a carbide. Nitrogen turns into a nitride. Oxygen becomes oxide. Fluorine turns into fluoride. Phosphorus turns into phosphide. Sulfur into sulfide. Chlorine into chloride. Arsenic into arsenide. Selenium into selenide. Bromium into, or bromine rather, into bromide, and then iodine into iodide. So all of these are the most common nonmetals you're going to deal with, and how they are changed into the IDE suffix. Now, going from the chemical formula to the chemical name is pretty easy, but what if we want to go the other way around? From the chemical name to the chemical formula. To do this, we follow three simple steps. The first step is to write out the symbols. So for instance, sodium, the symbol for sodium is Na. Whereas the symbol for chloride, well, it used to be called a chlorine, so the symbol for chlorine is Cl. Now the next step is to identify the valence charges. And these are the valence numbers, or the valence charges for all the elements that we will be dealing with, as well as the compound ions, the common ones and the 7 primary. If this was day school, then you would definitely have to memorize these for my course. However, because it's an online course, I don't mind if you use this sheet on our exams and also on our midterms. However, if you are planning on taking grade 12 university chemistry, or planning on taking a chemistry course in university or college, you will definitely have to have all these numbers memorized. And I'll show you how to memorize them, or rather how I memorize them. So looking at sodium. Sodium, if you look on this sheet, sodium, so it's in alphabetical order, has a valence charge of 1 plus. So I'm just going to use a little rough work and just write a 1 plus at the top, meaning it has a positive 1 charge. Chlorine, on the other hand, under C, has a 1 minus charge. So I'll write a 1 minus at the top. Now this is just rough work. You don't have to write it up there if you don't want to. I do it just to show you what I'm thinking about when I'm doing these questions. So why does sodium have a 1 plus charge? Well, if you'll remember, in order to become stable, an element needs to have a full valence shell. So sodium has two options. It can either lose this 1 valence electron and then has this full outer shell, because this shell over here disappears. Or sodium also has the other option of gaining 7 electrons. But what's easier, gaining 7 or losing 1? Now, when you lose an electron, you turn into an ion, right? And because electrons are negative, by losing a 1 negative charge, you are now a 1 positive charge. You're more positive by 1. And that's why we have a 1 plus charge over here. Chlorine, on the other hand, has two options. It can either lose all 7 of its valence electrons, or it can gain an extra valence electron. And by gaining that electron, because it's easier to gain 1 than to lose 7, it becomes more negative by 1. Because you gain an extra electron, electrons are negative, so you have a 1 minus charge, hence the 1 minus charge over here. So hopefully you have noticed that everyone in group 1A over here contains a 1 plus valence charge. Hydrogen, lithium, sodium, potassium, 1 plus, 1 plus, 1 plus, 1 plus. Because they need to lose 1 electron to become stable. And by losing a negative electron, you are more positive by 1. And then all the elements in group 2A have a 2 plus valence charge. Barium, beryllium, magnesium, all 2 plus charge because they need to lose 2 electrons to become stable. Then we jump these guys because these are the transition elements. They don't follow the pattern very well, so we can't really look at it in that sense. However, we jump over here to group 3A, and they should all have a 3 plus valence charge for these guys. So to recap, in general, group 1A elements have a 1A valence charge. Group 2A, 2 plus, 3A, 3 plus. Now group 4A, that's where things get a little weird because now you have a 4 plus or 4 minus charge depending on the situation. The reason behind that is because with carbon, for instance, it has 4 valence electrons, and in order to become stable, it could lose all 4, which means it will get a 4 plus charge, or it could gain 4 more, which means that it'll be a 4 negative charge over here. So since it's in the middle, it could go either way essentially, by losing 4 electrons or gaining 4 electrons, depending on which element it is bonding with. But in general, if the carbon is in the front, then it should have a positive charge. If the carbon is in the back, then it should have a negative charge, because usually it always goes the positive cation first, then the anion, the negative anion next. So if you see one of those group 4A elements in the front, then you would assume that it loses 4 electrons, it has a positive charge. If it's in the back, then you assume that it gains 4 electrons because it's in the back. So these guys have a 4 plus or 4 minus charge depending. Now once you cross this border line over here, alright, that's when you start to turn into negative valence charges. So this is group 5A. They tend to have 3 minus valence charge. Looking at nitrogen, which is in group 5A, it has 5 valence electrons, and in order to become stable, it can gain 3 electrons to have that full valence shell. Or alternatively, it could lose all 5 of its outer electrons to become stable. So what's easier, gain 3 or lose 5? Obviously gaining 3 electrons is easier, and so it has a 3 negative charge because the electrons are negative. Same thing with group 6A. They tend to have a 2 negative charge because they need to gain 2 electrons to become stable. And 7A they need a 1 minus valence charge because they need to lose one, or gain 1 electron rather, in order to become stable. So if you take a look at it, group 1, so it goes 1 plus, 2 plus, jump over here, 3 plus, then at the borderline here, plus minus 4, depending on the situation, then goes back to the negatives. Negative 3, negative 2, negative 1. 1, 2, 3, plus or minus 4, negative 3, negative 2, negative 1. And congratulations, you've just memorized all the monovalent, well rather mostly monovalent elements on this chart over here. So half your job is already done. The exceptions, of course, are silver and zinc. Silver has a 1 plus charge, zinc has a 2 plus charge. I remember this one because Ag, 1, Z is 2, A to Z, 1, 2. I mean, it's not much of a memory device, but it works for me. The reason why these two don't follow the pattern is because they exist in the transition element section of the periodic table. So they don't follow these patterns very well. So these ones you had to memorize yourself. 1 plus charge, 2 plus charge. So, quick recap. Group 1A elements, 1 plus charge. Group 2A, 2 plus. Group 3A, 3 plus. Group 4 is where the division begins. You have plus and minus 4, depending on the situation. Group 5A, 3 minus charge. Group 6A, 2 minus charge. Group 7A, 1 minus charge. When you get to the noble gases, though, they don't generally have any valence charges because they're already stable. They have a full valence shell. They don't need to lose or gain electrons. And because that doesn't happen often, they don't have a charge. So now you know where these valence charges come from. Let's continue on with our lesson. So, write out the symbols. Check. Identify the valence charges. Check. Next, insert subscripts. So if you recall, subscripts are numbers at the bottom and to the right of each element that denote how many of each atom is involved. Okay, so in order to figure out what the subscripts is for each element, we need to follow the zero-sum rule. So the zero-sum rule states an ionic compound is generally most stable when its overall valence charge adds up to 0. That's the key term. All right, must add up to 0. So here we go. I've got a 1 plus charge because I have 1 sodium. And I've got 1 minus charge because I have a 1 chlorine. If I add these two numbers up, what do I get? 0. So it follows the zero-sum rule. So this is stable. I don't need to add any numbers or any subscripts to any of these elements because they are overall charge of 0, and so they are considered to be a stable compound. So let's try our next example, magnesium bromide. First step, write out the symbols. Symbol for magnesium, Mg. Bromide used to be called bromine, so the symbol for bromine, Br. Next step, identify the valence charges. Magnesium is located here in group 2A, so therefore its charge is 2 positive. So I'll write down 2 positive over here. Of course, if you're not sure, you can always double check. Magnesium, Mg, 2 plus. There we go. Next one, bromine. Bromine is located here in group 7A. Oops, if I can write A there. So remember, it goes 1 plus, 2 plus, 3 plus, 4 plus or minus, negative 3, negative 2, negative 1 charge over here. So I write a 1 minus over here. I can also double check bromine, 1 minus charge. Good to go. So that's all set. Next, insert subscripts, follow the zero-sum rule. So right here I've got a 2 plus charge. And over here I have a 1 minus charge. If I add them together, do I get a 0? No, I don't. I get a positive 1 charge overall. That does not follow the zero-sum rule. So that means I need more of certain elements over here. So do I need more magnesiums? Well, that's not going to help me because I want to get rid of this 1 plus charge. But on the other hand, if I have another negative over here, an extra 1 negative, well then 2 positive, 2 negatives over here turns into a 0 charge, which means that instead of just having 1 bromine, I need 2 bromines over here in order to stabilize this and follow the zero-sum rule. And now we are following the zero-sum rule. Check mark. And at this point I can just erase this extra information here. And there we have it, the stable compound, magnesium bromide. I don't need this one at the top. This is my final answer over here. MgBr2.